In this video, I want to do a few examples of using differential notation. So here we're asked to use the notation of differentials to write the approximate change in the following function, given a small change in dx. Now remember, differential notation is just a change in derivative notation. Rather than writing things as dy over dx equals f prime of x, we're going to write these equations in the form of dy is equal to f prime of x dx. But to do this, we're going to need to find the derivative. So let's find the derivative of f of x equals 3 cos squared of x. It's going to be helpful for us to first rewrite the given function as 3 cos of x squared. And now we're going to differentiate this function using the chain rule. The derivative of the outside function is 6 cosine of x, and the derivative of the inside function is negative sine of x. And that simplifies into negative 6 cosine of x times sine of x. Now this is the derivative, and we could stop here. But if we want to be really sharp, we could simplify this further using a trigonometric identity. If we factor out a negative 3, we get negative 3 times the quantity 2 cos x sine x. And by our trigonometric identities, we know that 2 cos x sine x is the same thing as sine of 2x. So the derivative is negative 3 times the sine of 2x. Now let's use that derivative to write this in differential form. The derivative, which is dy over dx, is equal to negative 3 sine of 2x. And to go from derivative form to differential form, we just multiply both sides of the equation by dx. That gives us dy is equal to negative 3 sine of 2x dx. Let's do the same thing for this function. F of x equals 1 over x cubed. Let's rewrite 1 over x cubed as x to the negative 3, and now find the derivative. So dy over dx, the derivative, is equal to negative 3x to the negative 4th power. Let's simplify this a little bit by getting rid of the negative exponent. So dy over dx is equal to negative 3 over x to the 4th. Now let's write this in differential form. Multiplying both sides by dx gives us dy is equal to negative 3 over x to the 4th times dx. Okay, so why is understanding the relationship between dy and dx and the derivative so important? Let's look at this example. Here we're asked to approximate the change in the volume of a sphere when its radius changes from r equals 5 to r equals 5.1 feet using the formula below, and we're going to round to 3 decimal places. The volume as a function of the radius is equal to 4/3 pi r cubed. Let's find the derivative with respect to the radius, because the derivative will tell us how we should expect to see the volume change as the radius changes. The derivative of the volume with respect to the radius is 4/3 times 3 pi r squared. Now let's simplify this. So the derivative is 4 pi r squared. And now, because we want to know how the volume changes as the radius changes from 5 feet to 5.1 feet, let's write this in differential form. And that gives us dv equals 4 pi r squared dr. To do this, we're just going to plug in 5 for r because that's our original radius. And then for dr, we're going to substitute 0.1 because the change in the radius is 5.1 minus 5, which is 0.1. So our change in radius is 0.1, and that's going to affect the volume. How? Well, let's do the calculations. 4 pi times 5 squared gives us 4 pi times 25, which is 100 pi, and we have to multiply that by the change in the radius, which is 0.1, and that gives us 10 pi, and using our calculator, we'll find that 10 pi is approximately 31.416 cubic feet when rounded to 3 decimal places. This means that at the moment the radius changes from 5 feet to 5.1 feet, we should expect to see a 31.416 cubic feet increase in the volume.